Continuing chapter 10, I'm going to work a couple problems with you so you can kind of see how to do these. And I'm going to pause through a lot of this and then show answers. So again, kind of work at your own pace here. So if I have a mixture of helium and oxygen used in a scuba diving tank to prevent the bends. For a particular dive, I have 46 liters of helium at 25 degrees Celsius, 1 atmosphere, and I have 12 liters of oxygen at 25 degrees Celsius, 1 atmosphere. We're pumped into a tank with a volume of 5 liters. Calculate the partial pressure of each tank and the total pressure in the tank. So again, your go-to is always going to be PV equals nRT, okay? In general, that's going to be the gas law that you use. But I'm going to show you how to solve this two different ways, and I will show you that here in a second. So using PV equals nRT, I could find the number of moles of helium and the number of moles of oxygen. So I plug it in, and I find that I get about 1.9 moles of helium, 0.49 moles of oxygen. Then, once I find the number of moles, I can find their individual pressures. So I could plug it back into PV equals nRT, but now we're putting it into a 5-liter container. So here we were talking about the volume before, and then now we're putting it into a 5-liter container. So I end up with a pressure of helium of 9.3, pressure of oxygen is about 2.4, so the total pressure in the tank is about 12 atmospheres. So that's one way you could do it. A lot of, 2 steps to it. So let me show you the next way you could possibly do that. So because they're at the same temperature, if you notice they were all at 298 Kelvin, and the R is always going to be the same. So really what you're changing here is pressure and volume, okay? So if I wanted to know the individual pressures, I could use what we call Boyle's law. And again, you don't need to know that, but you do need to know that pressure times volume is an inverse relationship. So if I take the ATM, the initial pressure, and the initial volume, what is my new pressure if I put it in a 5-liter container? And you could do the same exact thing for oxygen. Now again, this is 9.2 versus 9.3. Again, there's some rounding issues here or there. But again, either way to solve this problem is going to get you to answer. But I like to show you multiple ways sometimes just because it might save you some time. All right, so the next problem I want to work gets into a lot of different things, especially some gas procedures that you're going to see in the book and also when we do labs. So I have a sample of solid sodium, potassium chlorate. So that's the solid that's in this test tube. It's heated and decomposes into potassium chloride and oxygen. And I'll write an equation here in a second. Then the oxygen is produced and it's collected through what we call water displacement. So this container was at the start of the experiment filled up completely with water, and then as the gas bubbles through it, it pushes down the liquid into this other container, and then the distance between where you are displacing it is going to be the volume. So this happened at 22 degrees Celsius. I got 754 torrs. The volume of the gas collected is 0.65 liters. The pressure of water is 21 torrs, and I'll explain that. Calculate the partial pressure of oxygen in the gas collected and the mass of the potassium chloride in the sample that was decomposed. So this is a pretty typical problem you see even on the AP test. So I'm going to pause and write down a couple things and then come back and explain it to you. So what I did over here was I wrote the balanced chemical equation. So I have KClO3 is decomposing into KCl, potassium chloride, and oxygen. It's a 2 to 2 to 3 relationship. The other thing I want to point out is when you do a gas collection through water, what happens is as the gas is flowing through the water, you end up getting some water vapor as well in the container that you're collecting. So you're going to have the gas and then water vapor. And so that is why you will always get the vapor pressure of water at that particular temperature. So either I'm going to give you a table or you're going to get that information. So that's what that 21 torrs is about, because water naturally will go to vapor at that temperature is going to be that particular amount. So that is why I have to use essentially Dalton's law here to figure out what my pressure of my oxygen is. So the pressure of the oxygen is due to the oxygen plus the water, and I know my total pressure, so that was given in the problem. So anytime you see total pressure, you need to think, oh, there's got to be a mixture there. So I put the 21 torrs in for the pressure of water, and I end up with 733 torrs, but I'm gonna convert that to atmospheres. You could keep it in torrs, but just know when you use the next equation, you have to use a different R. So I like to do everything in atmospheres. It's just my personal preference. So that has given me the partial pressure of the oxygen gas, but I still don't know the mass of the potassium chloride that it came from. So why this is such a popular problem on the AP test is then this becomes kind of a stoichiometry question. I can find the number of moles of oxygen now because I have its pressure, I have its volume, I have R, and I have a temperature of 295 Kelvin, 22 degrees Celsius. So I can easily find my number of moles once I have the pressure, okay, using PV equals nRT. Well, where it gets fun and exciting is the fact that since I have the number of moles of oxygen, I could go back to my balanced chemical equation. I say, well, for every 3 moles of oxygen, I have 2 moles of potassium chlorate. So I could set up my mole fraction as 2 moles to 3 moles, and then I could convert it back to grams, and my final answer is about 2.12 grams of potassium chlorate. So that's why this is a very popular problem on the AP test, because it incorporates so many cool things that you don't normally get in every type of problem. But it gives you the lab procedure, it gives you gas laws, you have to do some calculations, and then you also have the stoichiometry. All right, so next problem in your packet is this one, okay? And this one was from an old AP test. Typically on the AP test, the first couple parts of a problem are a little easier than the last parts of the problem. So the A through D, it gets progressively harder. So on a humid day in the tropics, when air is 35 degrees Celsius, a 20-liter sample of air was collected at the pressure of 1.05 atmosphere. The sample was dried by passing it over salt, which removes all of the moisture. The mass of the water removed was 0.75. So how many moles, total number of moles in the sample, what is the mole fraction of water in the air, and what is the pressure in the air? So I'm going to pause it and then come back with the answer. So of course I was given so many grams of water, so I could easily convert that to moles. That's just a simple stoichiometry problem. Then the number of moles of total number of moles of sample of the air. If I have the total pressure, I have the volume, I have R, and I have the temperature, I could get the number of moles of the air, okay, using PV equals nRT. Then again, going into more complex parts of this problem, mole fraction of the water in the air. Well, if I know how many moles of water I have, and I know how many moles of air I have, I could easily just do one over the other. And again, mole fractions are always going to be a decimal with no units. So I will have a final answer of 0.051 as my number of, as my mole fraction of water. And really where this comes into play is if I have my total pressure of the air is 1.05, I could figure out what is the pressure of the water based on if I know my mole fraction of the water. So all I got to do is take the mole fraction times the pressure to get the individual pressure of the water, again, the humidity in the air. So again, with these types of problems, it's just trying to get you to figure out which equation you need. But do note, just for future reference on the AP test, if you get part B wrong, if you follow it through with C and D on my test and on the AP test, you're going to get full credit. So anytime you're doing these calculations, please show at least a basic setup so I could see where you got your numbers from. And then you could round and do other things and skip some steps if you needed to. But that's true on my test and true on the AP test.